Okay, guys, we're going to talk now about molecular compounds. And molecular compounds are hydrogen and any other nonmetal that are in groups 4, 5, 6, and 7. They want to be a noble gas. They want to stabilize and have a full valence shell. And they're going to do that by sharing electrons. There's no electron transfer here. They will not become charged ions. They're going to just get close to each other and share to form a more stable electron configuration. So they're going to follow the octet rule, which means they all want to have 8 except for helium that wants to have a duet because only 2 electrons can be held in the first energy level, okay? So when atoms share one pair of electrons to form a covalent bond, it's called a single covalent bond. In every bond, there will be 2 valence electrons being shared, okay? And we call that a shared pair. So we will represent that with a dash. If they're not attached to another atom, we refer to them as what's called an unshared pair or a lone pair. And I'll be showing you that as we go forward. At the front of your packet, you will have the front page shows all the different configurations and geometric shapes that molecules will take that you are responsible for memorizing. Okay, and I'll be really clear as we go forward on which ones that we need to make sure we have. The second page in the packet is a thinking map that shows a step-by-step process of how we're going to solve and how we're going to decide to draw these molecules. So if you'll take that page out of your packet and place it where you can see, you'll also need your periodic table beside you. And we were going to follow that. I'll be referring to those steps as we go forward together. Okay? All right, so we're going to look at this first one. And this is a diatomic molecule. This is hydrogen. And of course, hydrogen's a nonmetal. It's a gas. And so when you look at your thinking map, the first one says, analyze the molecule. Make sure that they're all nonmetals. So hydrogen is a nonmetal, so we can go to number 2. Number 2 says, add up the total valence electrons. Well, hydrogen's an alkaline earth family. It's in family 1A, so it has 1 valence electron. And we see that there's 2 in the compound. So we're going to say that there's a total of 2 valence electrons. All right, and then those 2 valence electrons, we've already learned that the electrons travel in pairs. So we're going to pair these up, and to pair them up, I'm going to divide by 2. Okay, so right now on my thinking map, I'm at number 3. It says determine the number of bonding pairs. You take the total valence electrons, you divide by 2, and that's going to tell us that we have 1 bonding pair. That means we have 2 electrons in that bond. Okay, so at this point, it says on number 4 on your thinking map, it says distribute or give a bonding pair to each terminal atom. So I'm going to put my structure on the paper. Oops, sorry about that. Let me fix that. I don't want to go that large. Okay, so I put hydrogen on and the second hydrogen on. Now remember, we're trying to see how are these molecules made. Okay, and what shape do they take? So we're going to use this 1 bonding pair and we're going to connect our structure like number 4 says. Okay, so I used it, so I'm going to subtract it, and now I have no more electrons left. All the electrons are on my drawing. So then I back away and I look at my drawing, and I need to see if every atom is satisfied with its duet or octet. Remember, hydrogen wanted a duet. It can only hold up to 2 electrons on the first energy level. So what I need to ask myself is if each atom is happy. So does this first hydrogen have access to 2 electrons? Yes, it does. It has 2 electrons in the bond that's attached. So this one is happy. Okay. Then I look at this atom and I say, does this atom have access to 2 electrons? Even though they're the same electrons that the other one is sharing, That's the point. They're sharing. So this one has access to 2 electrons. So we are finished. We have all our electrons on the paper. We see that everyone's duet or octet is satisfied. And so we can now say that this is a linear structure simply because we know that 2 points is a straight line. Okay? All right. Obviously we did not use all the numbers on our thinking map. We're just starting with the very easiest one to draw, and we'll just go through these steps each time. Okay? All right, so now we're looking at chlorine gas. All right, chlorine gas is a diatomic molecule. All right, and we're going to count up its valence electrons. So we look at our periodic table, and chlorine has 7 valence electrons. It's a halogen, and it has 7 valence electrons. We have 2 of them, which means I have 14 valence electrons. I'm going to partner them up because we have learned in Unit 3 that electrons are always in pairs. All right, and we're going to say that 14 divided by 2 is 7 bonding pairs. Okay, I'm going to put my structure on the paper, 2 chlorine atoms. Okay, and I'm going to do what number 4 in my thinking map says. It says to connect the structure by distributing a bonding pair to the terminal atoms. And the word terminal means the ends. So I want to connect my structure. So I used 1 bond, so I'm going to subtract the bond that I used. So I used 1 bonding pair, and that's going to leave me 6 as a remainder. On number 5, it told me to subtract the lone pairs used from the total, and I did that. And then it says remaining pairs for lone pairs or turn into lone pairs or what we call unshared pairs. Okay, so these are lone pairs, and these are paired. So I want you to watch. This is 1 pair, 2 pair, 3 pair, 4, 5, 6. So I used them all. So all my electrons are on there. And the reason these are lone pairs is there's not another atom to attach a bond to. So that means they're just lone pairs are just unshared electrons that are just sitting around as valence electrons in pairs. Okay? All right. So now I've got all my electrons on the paper. I'm out of electrons. So I need to see if everyone is satisfied with their octet. So chlorine would like to have 8, access to 8, and they have 2 in the shared pair. They have another 2 here, another 2 here, another 2 here for a total of 8. So this one is satisfied. This one also has the 2 that's shared between the chlorines. This 2, 2, and 2. So this one has access to 8 electrons. So they're both happy. Okay, so we can say that this also is a linear structure simply because 2 points create 1 line. Okay, all right, let's see what happens with this molecule. So we're going to start with number 1 on the thinking map, analyze the molecule. This is hydrochloric acid, and it's all nonmetals, so I'm going to proceed with this covalent bonding steps. Okay. So I'm going to add up the total valence electrons. Hydrogen has 1, chlorine has 7, so I have 8 valence electrons total. So I'm going to take the 8 valence electrons, I'm going to divide them by 2. That means I'm putting them in groups, I'm putting them in pairs. All right, so I have 4 bonding pairs. So I'm going to put my structure on the paper. And I'm going to use 1 bond to connect the structure. So I have 3 remaining, and those turn into lone pairs. Now, I need to put the lone pairs, I'm instructed on the thinking map to put the lone pairs on the terminal atoms. Now, the problem with this is I can't put any lone pairs on hydrogen because hydrogen only needs a duet. And it has a duet with the bond that's here. So you never put lone pairs on hydrogen when there's a bond there because it has its max capacity. So if hydrogen's already happy then and satisfied with its duet, then chlorine wants to have the rest of them. So all 3 lone pairs go to chlorine. So I know hydrogen's happy with 2 that are in here. And chlorine is happy because it has 8. So this is also 2 atoms with a line in between. So this is a linear shape. Okay, so I had used all 3 of those lone pairs, so I'm out of electrons. And I should have done that before I drew my structure. Okay, all right. So these are the easy ones. These are the 3, these are what we call diatomics. This one's an acid on the far right. But these are just straight linear, easy molecular compounds to draw. All right, so when do we create multiple bonds? All right, so oxygen gas is a diatomic molecule also. So I'm going to go through my thinking map. Number 1, analyze the structure. Is it all nonmetals? Yes, oxygen is a nonmetal. So I'm going to proceed. Number 2 says add up the total valence. There's 2 oxygens, each have 6. So there's 12 valence electrons. So with 12 valence electrons, I'm going to put them in their pairs by dividing by 2. And I'm going to have 6 bonding pairs. Number 4 on the thinking map says, give a bonding pair or connect your structure. So I'm going to put my oxygens on the paper, and I'm going to use a bond to connect them. This bond, I'm going to subtract it, and that leaves me 5 lone pairs because it says to the remainder turn into lone pairs. So I'm going to put my 5 lone pairs on. So here's 1. Here's 2, 3, 4, 5. Okay, so I used all 5 and I'm out of electrons. I can't create any more matter. I'm pretty awesome, but I'm not that awesome. So I need to step back and look at the drawing and see if every atom is satisfied with its octet. So let's look at this oxygen. This oxygen has access to 8 electrons. 2 are in the bond. And then there's 3 lone pairs. So this one is happy. The problem is this other one to the right is not happy. It only has access to 6 electrons. So when you are out of electrons and there's no more electrons to give, and you see that one of the atoms is not happy, what you need to do is you need to do what's called share. Let me build this back up. Sorry about that. Okay, so what we're going to do is we're going to share. So when this happens, I want you to erase the one that has the most is going to share. So you're going to erase a lone pair. Sorry about this. Learning how to use my pen. So I'm going to erase one of the lone pairs. It doesn't matter which one. And then I'm going to change it and make it a double bond. You only make multiple bonds when you're out of electrons and one of the atoms do not have enough. So the one with the most has to share. So you'll change a lone pair, 2 dots, and you'll make it into another bond. Okay, so now let's see if they're happy. This one over here has 2, 4, 6, 8. Happy. This one also has 2, 4 in the middle bonds, 6, 8, and it's also happy. So now we know we're done. But there's a little bit more. On this structure, we have to be really careful because there's what's called repulsion fields. These lone pairs and these bonding pairs are electrons, and electrons are negatively charged. So they're going to repel each other here. They're going to be fields of repulsion here. So this molecule is actually going to look like this. These lone pairs are going to run away from that double bond and repel. And the other one's going to run away. And they're going to get as far away as they can without breaking connection. Okay? So they're going to move to about 120 degrees away from each other. And I know that because its circumference is 360 degrees. And there's 3 interruptions. There's a double bond and 2 lone pairs. So there's fields of repulsion here. There's 120 degrees, 120 degrees, 120 degrees. They just, like charges, repel. So they're going to move into that position. You need to demonstrate that repulsion in your drawings. So this would be your final answer. Okay? All right. Let's do nitrogen gas. All right. So nitrogen gas, each nitrogen has 5. So there's 10 valence electrons. I'm going to take the 10 valence electrons, I'm going to divide them by 2 and partner them up. I have 5 bonding pairs. I'm going to put my structure nitrogen atoms on here. I'm going to connect with 1 bond. So I'm going to subtract that bond and the remaining turn into lone pairs. I'm going to place the lone pairs onto my structure. Okay. And on these structures, I'm going to subtract it out, and I see that I'm out of electrons. So I can't add any dots or bonds. I've got to work with what I have. And I know they're not satisfied. Neither nitrogen on the left or the right have access to 8. When you're out of electrons here, and you have everything on your paper, and you don't have enough to satisfy everybody's octet, this is when you will erase lone pairs and create a multiple bond. So I'm going to erase this lone pair, and I actually erased more than that, and I'm going to draw a bond. So now the nitrogen on the left has access to 6 now, and the one on the right has access to 8. So it's happy, but the one on the left still is not. So I'm going to erase the dots. Sorry, y'all. I took the dot lone pair from the bottom, and I'm going to make another bond. So now, if I look, each bond holds 2 electrons. Each one of these nitrogens has access to 8 electrons. So they're both satisfied. So now you can say that nitrogen gas has a triple bond. But we're not done yet. The problem here is that the repulsion theory, this is a really strong, a really forceful negative field. So I'm going to draw it correctly. I'm going to put my triple bond here. And these up here, they are not going to want to be that close to that negative field. They're going to run as far away as they can from that triple bond. Okay, so this is my final answer, and it's linear. Okay, all right, moving on. Let's talk about water. Okay, the total number of valence electrons for water, we have 2.
Miss Terry, can you please send Izzy to the upper school office?
She's next door in the college room. Okay, so we have hydrogen has 1 each, and there's 2 total. So 1 plus 1 plus oxygen has 6 valence electrons. So we're looking at 8 electrons. So I'm going to take the 8 valence electrons. I'm going to partner them up, and I have 4 bonding pairs. So I'm going to put oxygen in the center. How do I know to put oxygen in the center? I can't put hydrogen in the center because hydrogen can only hold a maximum of 2. So it's always going to be the terminal. It's always going to be on the ends. Other than hydrogen rule, you're going to know to put the least electronegative atom in the center. Okay, so the least electronegative would go into the center. So I'm going to place my hydrogens on the paper, and I'm trying to decide, how are these atoms arranged? How are they structured? What is the shape they take on? Okay, so I have 4 bonding pairs. I'm going to use one here to connect, and I'm going to use another this time to connect because I have 3 atoms. In the prior examples, we had only 2, but now we're getting more atoms. So we're going to connect them all together. So I'm going to take 2 of the bonding pairs away, and that leaves 2 lone pairs. Now, when you place your lone pairs, on the thinking map says put them on the terminal ends first, and when the terminals are full and satisfied, you'll put any remainder onto the central. Now, remember, we can't put any on hydrogen because hydrogen is full with the bond. It can only hold 2. So because the terminal atoms of hydrogen are full, I'm going to put the lone pair on the central atom. Okay, so I use them all. I'm out of electrons. Okay, so now we need to think about this repulsion. First of all, we need to see if everyone's happy. Hydrogen is happy because it has 2 in the bond. This hydrogen is happy because it has its duet in its bond. And oxygen has access to 8. So all of them are happy. So now I need to look and see, how is this thing oriented? So they have this rule that they want you to give a molecular formula for it. If your structure, and this is the first one we have seen today, if your structure has a central atom, and we do here because oxygen's a center atom, okay? So if it has a central atom, you give a capital A. If it has bonds, you put a capital X, and you say how many bonds are coming off of the central atom. So there's 2 bonds. And then it wants you to write a capital E, okay? If there's lone pairs, you're going to, off the central atom, you're going to tell them how many there are with an E. So I can see that there's 2 lone pairs. So this is its molecular formula. You're going to memorize the name of the shape with this formula. And this shape is called bent. Okay? So if I were to draw this as my final answer, and I'm looking at the repulsion, these are negative charge, these are negative charge, these have electrons in them, they're negative. So they're all going to repel each other away. So this structure is going to look like this. Ooh, it's gotten big. I probably did too big. Yeah, let me redo this. Okay, so we'll go. So the lone pairs are going to be up here. And then we're going to bring oxygen downward. They're going to all repel in fields of repulsion. There's going to be repulsion between here, 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 and here. Okay? So this is a bent molecule, and that's how we would draw, and this would be our final answer. Okay? I'm going to do one more. I'm going to do carbon dioxide. All right? So carbon dioxide, they're all nonmetals. So carbon has 4 valence electrons. Each oxygen has 6. So we have 16 valence electrons. 16 valence electrons into pairs would be 8 bonding pairs. I'm going to put carbon, it's the least electronegative. Oxygen, oxygen. I'm going to use bonds to connect the structure. So I used 2. So I have 6 lone pairs. All right. It says to put the lone pairs on the terminal atom first. Here's 4, 5, 6. So I'm out of electrons. So now I need to see if everyone's happy. So when I look at this first oxygen to the left, it has access to 8. It's happy. The oxygen on the right has access to 8. It's happy. Carbon, though, only has access to 4. It's not happy. So remember, when we're out of electrons, there's no more electrons to put in, and we have somebody unhappy, then people with the atoms with the most have to share. So we're going to take a lone pair from here, and we're going to move them into a double bond. I'm going to try to just erase this one part this time. Just the dots on my eraser. So I took those 2 away. Okay, so now this carbon now has 6, still not fully happy. So the other oxygen's going to have to share. So I'm going to take away this dot and this dot. And I'm going to add a double bond. So now carbon has access to 8. So it's happy. And both oxygens still have access to 8. And now I just need to draw it with the correct repulsion. Because remember, they're going to want to share, they're going to want to get away from each other. So my final answer will include the double bond, of course. And these lone pairs that are left, they'll want to get away from that double bond. So this is going to be a straight line because I can see that it makes sense visually that this would be a linear, but let me show you how you write the formula, okay? So the formula is going to be, yes, there's a central atom with carbon. Looking only at carbon, there are 2 bonds. You count double bonds and triple bonds as 1 bond unit. So X means how many bond units do you have. So I have 2 bonding units coming off of carbon, and I do not have any lone pairs on carbon. So I don't even write an E, because remember when you write the E, it assumes that there's 1 because we don't write ones. So AX2 is linear. So you would memorize that as linear. So this is my final answer. Okay? All right, we're going to be practicing in class. You can start and stop, and you can replay this video. Come in ready to go, okay? Oops.